In this video, I would like to show you how to convert between the full structural formula, the condensed formula, and the line angle or skeletal formula. So let's start with the full structural formula. I'm going to draw a structure that has 7 carbons, and I'm going to put a double bond in it. So we have 1, 2, 3, 4 carbons, a double bond to another carbon. And then that's 6 of them, and then we're going to have a branch coming out right here. So make it a little bit fun. And in a full structural formula, every bond is shown. So this carbon is going to have 3 H's. This carbon will have 2 H's. How do I know how many H's each one is going to have? Well, we know every carbon has 4 bonds, and so from there you can determine how many H's it needs. So this next one has 2 bonds currently, so I'm going to need to put 2 more by giving it some H's. This particular carbon here, if we count the bonds, it has 1, 2, 3, 4 because of the double bond, so it actually doesn't need any hydrogens at all. This carbon will need 3 hydrogens. We call that a methyl group. This carbon is going to need 1, and then this last one will need 3. So I've completed the full structural formula. Now what I need to do is I would like to convert this to a condensed structural formula. To convert it to a condensed structural formula, I look at each carbon and I collect how many hydrogens it has. So this carbon's got 3 hydrogens around it. So I'm going to write that as CH3. The next one has got 2 hydrogens. So I'll write that as CH2, CH2. I have a problem here. I have this extra branch. The branch I'm going to represent in my condensed structure in using parentheses. So I'm going to take this carbon, comes next, and then I'm going to use little parentheses next to it to show coming out of that carbon is a branch. So the CH3 is a branch. Then I have to put the double bonds. You can't eliminate double bonds in this structure. Then I have a carbon with 1 H and a carbon with 3 H's. There are other ways to do condensed structures. You could have left that branch hanging out up above. We often put them in one line. I think it comes from a long time ago when people just had typewriters. They didn't have nice computers that could represent branch structures easily. And so you could draw them, but when you went to put them in a paper or something, you had to type them out in a big line. So parentheses made sense. Sometimes what you'll see here is that if you've got repeating carbons where they have the same number of H's, you can just plop those into a parentheses as well. So you have CH3, and then I could put CH2 outside the parenthesis. I'll put a little 2 to let us know there's 2 CH2s. And then I have my C, CH3, double bond, CH, CH3. So this is getting much more condensed. So these are different ways of doing condensed structures. Now, the thing that really confuses students is you have to try and figure out, is the thing inside the parenthesis kind of a linker, just a condensed way of doing a longer single chain? Or is it a branch? Is it a branch that's going to sprout out? And what I tell students is go ahead and look at what's inside. If I look inside the first one, I see a CH2. How many bonds does carbon normally have is 4, and in this particular case it only has 2. So if I, for example, put it like this, I'm implying that there's 2 little spots where it needs to be linked up. So that's how I know it's a linker type thing. When I look at this particular parentheses, what's inside is a carbon with 3 H's. And so if there's 3 H's, then I know, oh, there's only one bond that I have to somehow create. And so I think of it as kind of a bouquet, and it's going to be stuck into whatever is the carbon right previous to it. So this CH3 is going to be stuck into the carbon right ahead of it. These CH2s are going to be linked on both sides to the carbon before it and the carbon after it. So that's how you do parentheses. The other thing that comes up are line structures, and I'm going to draw this particular line structure over here on the right. And so what I'll do here is I look and I see I have 1, 2, 3, 4, 5, 6 carbons all in a straight line. So I'm going to create a zigzag because that better represents the tetrahedral shape of the carbon as best we can flattened on a page. So you start, you put your pen down, that's carbon 1, 2, 3, 4. This is where I hit my double bond. I'm going to put my double bond here. There is some cis versus trans type thing that I didn't really put into this structure, so you'll learn about that later. I'm just going to go ahead and put the 6th carbon here for now. And so I have 1 carbon that's at the end of this line, 1 carbon at the end of this line, and at the start of the next one, carbon, 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 carbon. So I have 6 carbons here. And then I need my branch, which is coming out of the 4th carbon, so that's going to be here. So that's your line angle structure. Looks very simple. It does do a better representation of what the shape might look like in space. And so now the question becomes, how can I get from this back to the full structure? All right, so what I'll do is let's go ahead and try to redraw it over here on the right. So I'm going to put wherever there should be a carbon, I'll put a little carbon there I'm imagining the carbons right where they are. And then from those carbons, I figure out how many hydrogens do I need to sprout. So I see I have 1, 2, 3. I'm going to have to sprout here, 2 here, 2 here, none there. 1, 2, 3, 1 here, and 1, 2, 3. So I kind of have a template then for drawing my full structure. So I'm going to have C, H, 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 C, H, H, C, H, H, C with the branch and its H's. It's getting a little messy, my apologies. And then finally the last 3 H's. And so that's how you can reconstruct the full structure from the line angle, also known as skeletal structure.